And we're back. Today we are going to talk about entropy, which is the randomness of a system, and for our cases, the entropy or the randomness of reactions. And we're going to base that information off what we learned last unit in chapter 6, talking about energy. And we're going to combine these two chapters, 6 and 17, all together into one unit. So last chapter, we talked about the first law of thermodynamics, the fact that the energy of the universe is constant. And we talked about how much energy is involved in the change, if and when energy flows into or out of the system, and what form energy finally assumes. And so what we want to know in this unit is why a process occurs in a given direction. Okay, so first off, a process occurs based on two different things. The first one, kinetics, which we are going to talk about at the end of the year, and that has to do with how fast a reaction occurs. It's dependent on the pathway, meaning it is not a state function, whereas with thermodynamic functions like delta H, it's only based on the reactants and products, meaning the initial state and final state, meaning that the thermodynamics, it is a state function. It is only dependent on the initial and final states. It does not depend on the pathway we use to get there. Okay, and we're going to talk about whether a reaction is spontaneous or not. So what a spontaneous process means is that it occurs without any outside intervention. So, for example, the reaction from diamond to graphite is actually spontaneous. That's the thermodynamic part of this part. However, we know that that doesn't just happen automatically. That process is just very, very, very slow. So even though that reaction is spontaneous, it does not happen quickly. Some examples of spontaneous reactions, or examples in everyday life, are a ball rolling down a hill. A ball spontaneously rolls down a hill, but it does not spontaneously roll back up. Or a car rusting, the steel on a car rusts over time, and then it doesn't just magically unrust, it doesn't spontaneously do that. And then some examples that we'll use in chemistry, when a gas fills a container, it fills that entire container. It doesn't just get clumped up to one spot. Or if you have a hot and cold object, heat spontaneously flows from that hot to the cold object. Okay, and using that example of a gas filling its entire container is if you have two bulbs here and the valve is closed, you can open it and spontaneously all these gas particles will flow through to fill both bulbs. So it spontaneously expands to fill its container because it's more likely, there's more ways having the gas evenly spread throughout the container. It's very unlikely that once you opened up this valve that spontaneously all of the molecules would be in one side of the bulb, for example, the left side of the bulb. So what this is called, the spontaneous process, that each spontaneous process results in an increase in the entropy of the universe. And we indicate entropy by the letter S. And entropy is the measure of randomness or disorder of a system. And always the natural progression is from order to disorder. So an example of that is if you throw up a deck of cards and picking them up, you're not going to pick them up in the same order that they were originally in when they were in your hand. Or, another example of that natural progression from order to disorder are your dorm rooms throughout the year. At the beginning of the year, they're very clean, no clothes are on the floor, but by the end of the year, there's mold growing everywhere. Okay? So we use entropy to look at what it means is the number of arrangements that are available to a system in a given state. So that means the more molecules there are, the more spontaneous, or the more entropy that something has. Right? So in nature, it always proceeds to the highest probabilities of existing, and that means more entropy. Okay. So let's say, using our example from before, we have 2 bulbs, but now we just have 4 molecules. So there's 5 possible arrangements that can happen. 4 all in one side, 3 in one side, 1 in the other, or 2 in each. So each of these are particular arrangements, whereas a microstate is a particular arrangement. And so looking at these, the most probable is the one with 2 on each side. So in this first arrangement, there's 1 possible state where all of them are on the left side. In arrangement 2, where 3 are on the left, there's 4 possible microstates. In arrangement 3, there are 6, and then if we look on the opposite, so now 3 are on the right, now there are 4 microstates for arrangement 4, and 1 when all 4 molecules are on the right. So that probability depends on the number of ways, or the number of microstates in which the arrangement can be achieved. And so the fewer the molecules, the less possible arrangements. Like if we have just 2 molecules, overall, there's just 4 possible microstates. So for example, if we have just 2 molecules, the possibilities are both on the left side, 1 on each side. Flip those 2 molecules, 1 on each side, just on different sides, and then 2 on the right side. So that means if I asked you for finding the probability of finding both molecules in the left side of the bulb, there's 4 possible microstates, so that would be 1/4. Whereas here, altogether, our number of microstates, 1 plus 4 plus 6 plus 4 plus 1, when we have 4 molecules, altogether, the number of microstates is 16. So if I asked you, okay, what's the probability of having all 4 molecules on the left side of the bulb? That would be 1/16. So if we want to consider the probability of a certain number of molecules all being on one side, all we have to do is look at the number of molecules. So if we make that n, the probability that all are on one side, either the left or the right, it would be 1/2 to the nth power. So that's why with 2 molecules, 1/2 squared is 1/4. And we just did the one for, there's 4 molecules, 1/2 to the 4th power is 1/16. So if we look at this one, if we have an entire molecules, Avogadro's number, 6 times 10 to the 23rd, that number is so small, we consider it to be nearly impossible. Okay? So all of them going to one side is almost entirely impossible. Okay? So a gas expands into a vacuum because it has the highest positional probability states available to the system. So the opposite is highly improbable, meaning you're not going to have a gas that's spontaneously filling up its container, shrink down and go into one side of that container. And now, looking at these three different states, solid, liquid, gas, gas has the highest entropy because those molecules are farthest apart, and it has the largest volume in which those molecules can move. And it has a much greater entropy than liquid, where those molecules are much closer together. And then solids have the least because they're more ordered and they have a smaller volume. So one other state that we are not considering is aqueous. That would go right in there. So entropy increases upon mixing to form solutions if you're mixing solids and liquids into water. But then the opposite is true. If you are taking a gas and dissolve it in water, that means its entropy would decrease. So aqueous has less entropy than a gas. It's more restricted. However, in comparison to solids and liquids, it has more available volume and thus more available positions. Its positional probability is higher, meaning it has a larger entropy. Okay, so for example, if we're looking at some reactions, so the evaporation of alcohol, so evaporation meaning it's going from a liquid to a gas, that means entropy is increasing. And if entropy increases, that means the change in entropy is positive. So we would say for letter A, delta S, final minus initial entropy, that is positive. Then if we look at B, freezing, so we know that's the phase change from a liquid to a solid. So in this case, entropy is decreasing. So that means change in entropy, the final state minus the initial state, that entropy is negative. So here, delta S is negative. Then, letter C, you're compressing an ideal gas at constant temperature. So that means what you're doing, you are decreasing, so you're compressing it, so you're decreasing the volume, meaning entropy will lower, so the delta S is negative. Then the next one, you're heating an ideal gas at constant pressure. So constant pressure, and you know, okay, if you're increasing temperature, that means from Charles' law, you're increasing volume. And also it makes sense when you're heating something, those molecules are moving faster, meaning those molecules will have more entropy, there will be more randomness and more disorder. So delta S, so entropy increases, so delta S is positive. Then last one, dissolving salt, NaCl, which is a solid, in water. So you're going from something that's in a solid state to aqueous. So if you think about it, when salt dissolves in water, you're increasing the disorder because the salt dissociates. It breaks apart into its two ions, into its cation, sodium cation, and chloride anion in water. So therefore, its randomness and disorder will increase. So a couple other things with these reactions. Anytime you're going from a solid to a liquid to aqueous to gas, entropy is always increasing. But let's say you have in a reaction a solid going to another solid. It's dependent upon the number of molecules. So let's say in the reactant side you have one molecule, here you have two. In this case, entropy would increase simply because you have more molecules. And then let's say in a different reaction, let's say you had 3 molecules of gas on this side and 3 on this side. So if the states are the same and the number of molecules are the same, that means that entropy would also remain the same. So using these, we can get to the second law of thermodynamics, meaning that processes are spontaneous when they result in an increase in disorder, or essentially the entropy in the universe is always increasing. So we know from the first law of thermodynamics, the total energy of the universe is constant, but entropy is increasing. So same thing that we did with heat, the overall and energy. The overall entropy, the entropy of the universe, is the overall system plus the surroundings. So nature always moves towards the most probable state available to it, even though energy remains the same. So that means there's always an increase in disorder. Okay, so that means for the entropy of the universe, if that's positive, entropy increases. If it's negative, entropy decreases. And then if the change in entropy of the universe is 0, that means the system is at equilibrium, meaning the reaction has no tendency to occur. So if delta S is positive, the entropy is increasing, so that means that reaction will occur without outside intervention, so it is spontaneous. And then if entropy is decreasing, that reaction is non-spontaneous. Okay, that's all for today, and later this week we will talk more about entropy as it relates to reactions in chemistry.